So the presentation is, I'm going to go through a little bit of my background, where I came from growing up with computers, and technology, and my timing with respect to the internet and so on, because it's sort of on the crossover. You know, the current generation is digitally native, and sort of that's come to probably most of the people in this room later in life than the current generation. And I'm going to show a couple examples, just maybe like case studies really, I guess, for where we were able to very quickly kind of cull important information from databases on the internet and come up with interpretations that help us solve problems. So I'll show you a couple examples of that, and then after I go through a little bit of my background. So for the last 16 years, I've worked at Sandia National Labs, or one of the 3 nuclear weapons lab. So we're overseen by the National Nuclear Security Administration, which is part of the Department of Energy. We're the largest of the labs with just over 10,000 people on roll right now, about $2.5 billion a year organization. And right now, originally we were a division of Los Alamos during the Manhattan Project. We were Z Division, right here on at Kirtland Air Force Base, which was an Army airfield at the time. Now that's 40% of our funding. The other funding comes from other basic science research, what we call defense systems and applications, which is like other government agency work. So we are funded almost probably entirely by the U.S. government, a little bit of corporate work we do. So that's a little different than academic environment. We're almost certainly the most diversified lab. I mean, from a funding standpoint, that's good. If something gets cut, usually it's not everything at once. We do a lot of work in my particular area, material science. Really impacts sort of all of these areas. We get involved with the computing folks, with efforts in geology and national security. We have a pretty forward-looking philosophy, and so because we do a lot of applied work, we're interested in developing methods. So my research has been in developing techniques and methods for characterizing materials better, faster, more comprehensively. Okay, so that's a little bit about what I do now. Where I came from, my first computer, I found an image of that because we never had a picture of it. It's a TRS-80, Model 1, 48K RAM. Right, could do everything our current computers do. Word processing. You run a separate spell checker. We did have the floppy drive, no hard disk, by the early to mid '80s, we were on PCs, and that's the basic technology that's enabled my particular research area, where I want to analyze large spectral data sets. In college, it's the first time I saw a technical library. Right. We were using mainframes. The early first Macintoshes were there. I had a PC clone in my dorm room, and a 300 baud modem, so that we could dial up, and I could get access to the mainframe to work on various computer projects. I did actually start doing research as an undergraduate. Cornell had a very good program for getting undergraduates into research labs and getting experience. And then they send you into the stacks. These things go down 4 or 5 stories and have an interesting smell of old books, but no computers to do any of the accessing stuff. I mean, some mainframe stuff for maybe searching for tech, for books, but not really any journal databases, at least as available to the students. By grad school, that's the Gophers were one of the competing technologies that didn't win, right, for what became the World Wide Web. And very early internet, you still had to go physically to the library. There was no, by the end of my graduate work, which was '95, you could get, lists of papers maybe from search terms, but no full text. And only really a few years back. So this really, and I apologize that there are probably people here who know the history a lot better than I do, and so I'm not being a historical expert, it's my practical experience. By the time I got to LANL, this is really the first modern technical library. So when I postdoced at LANL in the mid-90s, we did have a lot of, now you could sit at your desk, you still went over to the library, but basically early on in that, you were just printing. You could search for papers, you print something out, You go to the library and you search for those papers, and then you decide, no, that's not really what I wanted. So there's a lot of wasted time in that. And still not much full text available. Early at Sandia, late 90s, you started to get full text available, and that really, was very useful. And it went back about 10 years. My recollection is it had about a 10-year history. Beyond that, you were going to the library. And not many years after that, I'm not sure exactly where that happened. By now we have everything available, very easily, and you don't ever have to actually go to the physical library. So, in the early 90s in grad school, I'd spend weeks in the library. You had the time because that's your job. You're going to become an expert on one little area, in my case, solid state chemistry and ceramics. And you could spend weeks in the library, following threads, looking at every paper, photocopying papers, collecting all the literature. I could have done all that now in an hour, pretty much. Not including the reading part, but I could have collected all the source works in about an hour. And, but today I don't have that time. You can't spend weeks searching for stuff. And we are pressed for time. We're more or less antisocial, introverted, however you want to, somewhere on that spectrum. So face-to-face, if there's an alternative to face-to-face, especially when it's so much more efficient at getting at what we want, which is scientific literature, then that's what we're going to do. So let's get into a little bit of that. Where have I published? So these are some of these are societies that self-publish, others are publishing houses. I didn't even realize that, I never really kept track of this until I had to give this presentation. The various places that work I've done has been published. And then in various research areas, I may be atypical, probably am atypical for scientists in that I've published, in very diverse fields, looking at not just materials, but geology, meteoritics, biology, so this gives me a footprint that's farther than just, say, physics or material science. All right, so my first go-to is Google Scholar. Fairly comprehensive. I mean, I actually really didn't research how this worked for me directly until I had to talk about it. I mean, I just used it. Now it has a few blind spots, but I didn't actually, so this isn't a research area for me. This is giving this presentation is sort of a one-off thing. So comprehensive, fast, and easy. It's sort of, to my view, it would appear to work just like their search engine. It is very fast. Compared to Web of Science, it's several orders of magnitude faster, which is important. You're going to go through a lot of different search terms, you're going to go through time periods, and it actually gets there faster, and with potentially more chaff amongst the wheat, but you don't have to register unless you want to track your own citations. For me, familiar, intuitive interface, right? You know how it works, and it's fairly easy to find your way in and find the various features that are for refining searches. They sort their hits by relevance, best match to search terms and time cited, as far as I can tell. And it finds patents as well as papers which have cited, say you're looking for a certain author, you'll find papers that have cited that particular author. For me, I did this as I'm using myself as an example here because I know the most about me versus any other scientist. And you can basically see your footprint in science very quickly. If you're looking for a new subject area, the first thing you're going to get is the most cited paper, right? If you say carbon nanotubes, 6,000, 12,000, 20,000 citation paper, that might be a good starting point. Maybe that's not the best paper, but it was certainly a seminal paper, and if it's cited by a lot of people, that's where you're going to start your search. And then you're going to drill down further and decide, now I really want to understand more about some other aspect of that, and you'll refine that to get, say, to mechanical properties of carbon nanotubes, for example, right? It's the way that one of the things I've used various tools for is to look at citation metrics, because our management wants us to track our footprint and our citation metrics as just one of the things they do in our performance review, how much we're publishing in any given year, and then something like an H-index, right? So I have used Researcher ID, and I was a little ignorant that Google actually will do this for you as well, and I'll show you some results because they come up with different, they see different parts of the world, and so let's see. Yeah, Web of Science, which is behind Researcher ID, misses some of my publications apparently because they're not in high impact enough journals, right? And I can't stand ResearchGate. I don't know if anyone here works with this. It is insidious. The little checkbox, invite all your co-authors to join, right? If you don't check that, right? It says, we found in one of your citations online. And then in the microprint, there's a little checkbox that says, invite all your co-authors to join ResearchGate. So that's actually how I got into there. And I put them in the junk mail because they send me 50 emails a week. Google Scholar finds a lot more citations, but it's also finding like conference proceedings which aren't in Web of Science, right? Because they're not proper journal articles. Okay. So I did this search. You could call it an ego search. People do this on Google as well to see your footprint on the web. And I don't own paulcatula.com. That's an artist in Colorado, by the way. But Google Scholar finds, just with that search term, 1,710 results. The best cited papers with where my co-authors have used my middle initial are found first. Recent articles with no cites are down in the 1,000 range. Like they're not relevant, and there apparently is no way to sort that. Your whole thing by date in Google Scholar. So that is, you come up with all these articles. You say search for this, and it comes up with by relevance numbers of citations. If you say sort by date, it only gives you the last year which is not the whole picture. So if you want to follow an author's history through. So that's a blind spot for Google Scholar as far as I can tell. It misses completely if my co-authors didn't use my middle initial. So that's an issue for if you're searching for an author's work and maybe the initials were used or not, you might be missing the whole amount of an individual's work. Yeah, if I did make an account finally, right, for Google, and I had them track my citations. They find everything from conference proceedings to patents and the like, all fairly accurate. And when I did that, they actually did find this difference. And I presume because I registered, and you tell your institution, Sandia National Labs, and they then say, well, if it's a P. Catula and he's at Sandia, then likely it's his, and it's up to the researcher to go through. But just the Google Scholar misses that because it apparently doesn't have that additional information. Yeah, like I said, you can sort by date, but it doesn't go all the way back, which is kind of a pain. Citation, AIP's product. I've only published about 1/10 of my papers in AIP, and my colleagues that are published on my behalf. I've only published about 10% in there. Google Scholar really sees the whole world, and if I'm on Sandia's domain, then we're IP addresses, then everything our technical library is subscribed to is available. So virtually everything that I published, I can find full text now online, just on one quick interface with Google Scholar. Okay. Now, interestingly, it's just I didn't understand that they see different things, but Google Scholar sees, for the same exact papers, sees about 100 more citations. And I don't really have the time to do a research project on the reasons for this. Maybe a few folks know, but I presume it's because Google Scholar is taking conference proceedings as well as journal articles, and really they don't discriminate against low impact factor journals. But it was quite a difference, and if you want a pumped up feeling for yourself, then you only use Google Scholar.
Paul, the one on the right is what?
This is
That's Google Scholar?
No, this is Researcher ID, Web of Science, right? So they find 244, and again, they missed some of my publications too, because they might have been published in a journal that's not a high impact factor enough. And they certainly don't capture conference proceedings, because those aren't even generally peer reviewed or to that level of a journal. but systematically. So these are the same basic papers. They rank them in the same way. This one has a difference of 50 citations. This one is a difference of 60 or so, and so on. So it's a, presumably because they track conference proceedings as well, which for my purposes we don't count as peer-reviewed publications.
Google Scholar also admits that they estimate.
They estimate.
And I don't know what that means.
Yeah.
I don't know that anybody does, but.
Well, and they like if you go a little further down, you'll find a few of my patents from the early 2000s. Who knew they got like a 70 or 80 citations, right? I mean, generally we will sometimes cite the patents because they predated the journal articles on the subject area, but I didn't really expect other people to necessarily cite patents. Okay, so then I found one article that crosses all these three, AIPs, citation, Researcher ID, and Google Scholar, and they all come up with different numbers for the same. This is published in an AIP, and I will say that once you're looking for this, I like this interface, the site, where you've got all the information in, and everything is linked, so you can follow all the subsequent citations. But pretty interesting difference. Presuming the AIP, knows how many times things are cited, but Researcher ID, this one is a little unusual, unless there's, why that's bigger. So it's a pretty big spread, though, in how the Google Scholar is definitely a little overly generous. Okay, so let me give it a couple examples now. So this is a recent example. Materials Research Society it's published by Cambridge Press. I was asked to join a few colleagues and do a review article on some work that I did, the original seminal work on 3D microanalysis. And I really hadn't followed all the development since. So, it's not unusual. You're first in, you develop a new technique. We use this in our lab, but we're not really publishing a lot on it this day. So I went back in and said, let's use a series of search terms and in an afternoon, right, including reading papers, because I want to know what to cite in a review article. See who cited my work. More generally, because this is a group in Switzerland who really doesn't like to cite my work, and so there's a little bit of a feud there. They think they did it first, but they didn't. Searching on some fairly general terms, it came down to, there were a fair number of articles, but only 6 that I really had to cite. So an afternoon of work on our what we call our Science Friday, which is our Friday off when you can do work that's not funded, because writing review articles we don't get paid to do. We do it on more or less our own time. So my time is important, so if I can get all this done and have a pretty good feeling that I've gotten a good sense of what's in the literature, enough to write a review article or flesh out the citations for a review article, then that's important to me. Okay, so you may not be aware, but Sandia National Labs was asked by the FBI in late 2001 to help out with the anthrax attacks right after 9/11, and partly because of technique development that was going on with me and myself and some colleagues, and capabilities the FBI didn't have in terms of physical signatures in bioweapon materials. Not that we have any chops in analyzing biological materials, but because we're looking for the kind of things that you look for in material science, chemical signatures, elemental signatures, for example. Okay, so a little timeline. This just 9/11 happens here, and then a bio attack, right? Letters are mailed, people are dying, mail facilities are quarantined. The Hart Senate office building is shut for decontamination, and basically they've got powder material from the attacks that looks a little different. Early material looks like kitty litter. Later material looks like fine powdery material. That they're very worried about, is this weaponized? Is it treated to flow more easily or disperse more easily? So we had to do a crash course in biology and spore physiology. So Bacillus anthracis is a spore-forming bacterium, and this is what the spore looks. This is the dormant state, so it has a cortex, a spore coat, exosporium, and these little hair-like features on the outside. So, we could, read a few articles or some general text on this and learn this. We're not, like I said, we're not biologists, so this wasn't something we would necessarily know to start. The other thing is the biologists like to treat their samples and fix them first with osmium tetroxide, which sterilizes it, so that then they can handle it in a regular facility. Otherwise, it needs BSL, Biosafety Level 3 facility, and they never handled it. They would never even handle it in a BSL-3 in powdered form if they didn't have to. So they're in BSL-4, like full respirators and all that. But they sterilize it with osmium tetroxide, and then they stain it with uranyl acetate. So throw uranium in it, and it sticks to certain parts of the structure, and a biologist looks at that and said, I can interpret that image. But they've totally messed up the chemistry of the sample by doing that. Even still, we still work with these, and then we work with them to refine their sample preparation to avoid things like that. So so I'm giving you a little science here, because I can't not give a presentation without some technical parts to it, sorry. So we looked at, we've got the Senator Leahy's material, Senator Daschle's material, and the New York Post material. And a fair amount of this material was collected in envelopes. That was a lot of material. So we identified a chemical signature associated with the spore coat. So this internal structure in here, right? And so that's interesting to us. We don't find any other extraneous material, really very clean from the standpoint of no pollen or no other junk or bits of salts that might have been used in the processing. And so we quickly came to a chemical signature. This then was briefed to the president by FBI Director Mueller. So take the technical side. They don't want to see that. The president wants to see the color picture. Okay. So a little bit of the backstory. Silicon oxide, which is also a dispersal agent for bioweapon materials. It's also a flow agent in pharmaceuticals and other areas. They did an early analysis in another government lab, which shall remain nameless, and they said, we see silicon. This has been weaponized, right? So that's a big question. Was this done in a sophisticated bioweapons lab, or is it plain vanilla material? It's lethal by itself, but it's has it been treated to be even more lethal? So we identified silicon on an internal structure, really doesn't interact with the environment, doesn't affect dispersal, and this is at a time where they're trying to pin this potentially on Iraq or other foreign governments, right? So, so then you look and you figure science, right? Science should get this right, and so there's this article in there. So this is literally weeks after that data was briefed to the president. It's leaked to the press. And they start coming up with all sort of half-baked theories. This unusual coating, a chemical compound unknown to experts, right? Probably also from Roswell or somewhere like that, right? And they come up with this term, polymerized glass. So we see polymerized glass and we go, let's see if there's any literature on that. Nothing. This is a made-up term that has no significance. It's not in any scientific literature. Wow. And these guys should know better, right? They have access to all this information, and so this is phase one, right? This is right after we're not allowed to talk about this material. We're quiet until 2008 on this, and after the FBI believes Bruce Ivins, who worked at USAMRIID, the U.S. Army's Infectious Disease Research Facility, was the perpetrator of the attacks. Circumstantial evidence, largely because he committed suicide, and they never found a smoking gun, right? But for our part of this was, we can show chemical signatures. We actually linked all the attack materials to a common preparation.
New questions tonight about the man accused of the 2001 anthrax attacks. The FBI said the case was closed months ago, but experts say some of the evidence is not an exact match. So is it possible the feds got the wrong man?
7 years after the attacks, the FBI claimed the science led to only one suspect, biodefense researcher Bruce Ivins, who apparently took his own life as the Bureau was closing in.
We have a flask that's effectively the murder weapon from which those spores were taken that was controlled by Dr. Ivins.
Joe Michael at the Sandia National
That's a
Labs
transmission
in
electron
Mexico is part of
microscope.
the science behind the FBI's case. Michael compared the bacterial spores in 3 letters with the bacteria found in Ivins' flask. The conclusion, they do not share the same chemical fingerprint.
I don't think this exonerates him at all. I don't think it's enough to say that he did it as well.
The powder in the letters contains silicon, oxygen, iron, and tin. The flask does not. Michael offered this explanation for why there is no chemical match.
What the FBI believes happened, and I think the evidence helps support them, is that this material was taken out of that flask and then regrown before it was put into the letters.
The recipe used to regrow the anthrax remains a mystery. Some critics still question whether Ivins, who worked as a microbiologist at Fort Detrick, was the only person who controlled access to the flask, as the FBI claims.
It doesn't appear that the FBI has an ironclad chain of custody here.
At Quantico, Virginia, a forensic examiner told Fox that the chemical mismatch is of no consequence because the powder and the flask share the same DNA. There is no expectation they should have the same chemical profile, Jason Bennett told Fox, acknowledging, "We don't know what method was used to grow the spores." This week, 2 congressmen, Jerry Nadler and Rush Holt, introduced legislation calling for the creation of a
So as it turns out, right, a spore is a dormant state, and that was what was stored in this flask in a liquid suspension, right, in Dr. Ivins' lab. And they did the genetic analysis and defect DNA analysis, and they found that they linked the attack materials, all the attack materials, to that flask, right? And our job was to say, is it treated? Is there anything else we can see? And it turns out there's a little more to the story of why that coating happens, the internal structure happens. But for fun, let's look at a different viewpoint.
Number 1, anthrax gate. As you know, under Mr. Bush, the FBI closed the case saying that Army scientist Bruce Ivins made them in a flask at Fort Detrick in Maryland, flask number RMR 1029, and then he killed himself. Well, maybe not. The magazine Nature now reports that at a biodefense conference this Tuesday, a scientist from the Sandia National Laboratories in Albuquerque presented analyses of 3 anthrax letters, the one sent to Senator Daschle, Senator Leahy, and the New York Post. They show anthrax mixed with silicon, oxygen, iron, and tin. Bruce Ivins' flask at Fort Detrick, good old number RMR 1029, contained anthrax, no silicon, no oxygen, no iron, and no tin. In fact, Ivins' entire lab at Fort Detrick showed anthrax, silicon, and oxygen, but no iron and no tin. The analyst cautions that the iron and the tin could have worked their way into the anthrax between its time in a flask, somebody's flask, and its time in those envelopes. You remember the anthrax attacks? Killed 5 Americans, sickened 17 more, September 19, 2001 till November 21st, 2001, thus falling into that time period after 9/11, the time George Bush and his apologists still insist he kept us safe.
A little different viewpoint, but he gets it wrong. Dr. Ivins' flask did indeed have spores with silicon and oxygen on the spore coat. We analyzed those materials. But let's do a little research. Now, this is a biological literature searching by someone with an 8th grade biology education. Come on, there we go. Okay, what do we find? In the early 80s, early analytical electron microscopes, so it's a transmission electron microscope with an X-ray detector, basically an older version of what we have today, right? They find a different bacterium, but a spore-forming bacteria that develops the same structure, basically from bioavailable cations. So elements in the environment are incorporated into the spore. They actually make the spore more robust to stand up to a low pH environment in an animal's stomach. So it passes into the intestine and then grows, infects the animal and whatnot. So right, very quickly, Journal Bacteriology, we can find this, you know, in just put silicon spore coat. Boom, right? These 2 papers come up as the top in that, and a bunch of other research since then. I mean, so the microbiologists who do, you know, spore-forming bacteria, they knew this, but yet the guys at Science didn't bother to check to see if there's some literature on this. I mean, it's so easy to do. You know, why not? And of course, you know, the media doesn't really necessarily do that kind of background, but you'd expect a science reporter to. And more recently, a Japanese group basically, did some more research on this. Another Bacillus cereus, but it's related. All the spore-forming bacteria will do this. If you can get a bioavailable form of silicon, it will incorporate other cations as well. So iron we found in tin were the sort of unique thing about the attack letters. But again, right, this is literally 5 minutes, and then read the paper, so we can find these 2 critical articles just on a very simple term without knowing anything else about biology or spore physiology. Okay, so to sum up, with the search things, nothing's perfect, but to me, Google Scholar is the best trade-off in terms of coverage, ease of use, speed. It sees everything. For me, it sees 1,700 things. A lot of that is conference proceedings down below, and but the most cited journal articles first. It directs you to all the other places, Royal Society of Chemistry, AIP, if that's where the articles reside. Our technical library has almost all of the subscriptions. There's a few we were missing, like IEEE, I think, has maybe Wiley. Some places there are black holes in that, and then we just ask the library to get us a copy. Google Scholar Citation Tracker is way more generous. I would tend to believe the Researcher ID one more, even though I'd like to believe Google Scholar. More journals, citations from proceedings, which are kind of questionable to track necessarily. More but not better. And there's really no excuse for spending 6 months in the lab instead of a trivial amount of time searching. And I think fairly few people actually do. Web of Science is a bit slow, misses some things, and really legitimate journals, not just this new pay-to-publish journals, which really we shouldn't be tracking, which aren't even necessarily peer-reviewed. And citation, it's limited to physics journals, right? For me, 11 out of 100 and something of my articles, and Google Scholar finds that anyway. So it's sort of like my portal into the AIP world is through Google Scholar, and just because it sees everything I may want to see, not just a small subset. So with that, try to answer any questions you guys might have.
Just Paul, do you have an ORCID?
A what?
I guess not.
There's another researcher ID database
that's
gaining some traction. RG has plenty to say about it. So I wondered if you had an ID with them or not. Answer my question.
I have 3 ORCIDs, just so you know.
What? To prove a point.
And why do I have 3 ORCIDs? Because I'm into author disambiguation, and I wanted to see if there was any, and there's not in ORCID. But ORCID is a big publisher consortium to try to gather all information about an author into one place.
Okay.
Against the great Satan known as Elsevier among the publishers. So, well, everybody has their own debates. Come on.
Well, I will say Elsevier is the only. I really dislike some of Elsevier's actions because, I review papers for various journals, and several of the Elsevier journals I'm a reviewer. Review a paper, reject it. There's real problems. They then take that paper and say, now they ask, but last year they did not ask. They just sent it to another journal with the reviews, and it got published with, they actually did make it acceptable to me. They took all the equations out because they had plagiarized our work, and one of my colleagues' work, and taken all his equations almost verbatim in the same order. And I said, you should investigate this as a potential plagiarism. I said, I'm not going to make that call because we're close to it. Maybe you could identify a third party, independent third party. They sent it to another one of their lower impact journals, and it got published sans equations. So that to me is letting them off too easy, right? If someone plagiarizes or
I did want to, Charlotte said that Google Scholar says they estimate, and they do estimate, but the reason they say it's an estimate is because they consider it to be an ever-changing number. So if you look today and you look tomorrow based on the Google rating stuff, it will change. So that's their liability cop-out.
Okay.
Just so you know.
This is related to that, but does Google track web page
citations, so if I have a web page and I put his paper on my web page about
Google
Silicon House,
does, but Google Scholar does not.
Yeah.
So, yeah, you need to differentiate the two. I think part of what Paul underscores is, I know for a lot of you, there's an issue of being sure that Google can track your papers at least to some level. And it's a quick way in.
Yeah, but I mean, without the fact that pCATULA doesn't come up when you do pgCATULA is a hassle having to do another search. I mean, once I gave it a little bit more information, my affiliation, it found at least all. I didn't go back as far as Los Alamos, but it tracked all of my pCATULA papers, right? So.
Other questions?
You might, it's only a specific section of the literature, but you might just out of interest find our article level metrics interesting to explore, because they do break out all the different kinds of dimensions that we were just talking about.
What's it called, Rachel?
Article level metrics. So they measure citations, page views,
Okay.
Tweets,
Facebook likes,
Yeah.
all subdivided.
Right. I've only ever seen that data because I'm on the editorial board for Microscopy and Microanalysis, which is a Cambridge journal. And if you go into there, and search for something within their interface, it shows you some of that metrics like views, and they do track that, but they don't really make it very public. I mean, it's not something that shows up, anywhere that I'm familiar with. So it's interesting to.
Yeah, I think with your interest,
Yeah.
I think you would find it interesting.
Mm-hmm.
It's like a little logo or image or something, but donut that's color coded, and it's pretty cool.
Yeah, you have to incorporate that
With the site, with the
your
impact
site.
factor.
No, it's not an impact factor
Well-
thing. It's working with all the metrics, and there's a bit of code that you can drop in on your site that hold the different pieces of information. But whoever's running the site has to develop, or has to do that, has to connect all those things.
Any other questions? Thank you, Paul. This is fabulous.